and you can find a magic words and see better results. But the counterpart to that is the statement that for any LLM, similar like this, to or Gemini, for any query that seems to work, you're going to be more answer. There are not human brain, human beings that will be fast, not what very much the counterparts are passing. And you know, to what extent having to again question you can grab understanding this very simple meanings. So besides that, there's a lot of detail about how LLMs can perform in context learning that to new problems in the cloud. And what really seems to happen is that LLMs are capable of fetching memorized programs that might be from us. And of course, they have access to millions, potentially, of memorized programs that discipline and the problem is that if you don't have a memorized program ready, if they have to face something like the family, no matter how simple, they may not be able to analyze it from a human. So like the task, none of the tasks any human can probably do this. Surprisingly, there's no element that can find an answer, no matter how many examples. Eventually, this will be attached the information. Conflict that's underlying issue adapting. And the last LLMs have generalization. Some examples include staff and their troubles, multiplication with list sorting, and so on. So they have to be aided by external tools to problems. So there was an interesting paper recently that investigates how LLMs handle computing. And it found that, well, actually they use it. So it's titled face-to-face additionality, and the authors found basically that LLMs do linear supermatch instead of actual prediction. There was another paper that was very surprising. The reverse occurs, and it's found that if this LLM something like Paris is the capital of France, it cannot automatically answer what is the capital of France. So that's actually very surprising when you get familiar with. One thing to keep in mind is that failure cases and the specific queries I'm showing you right tend to be fixed relatively quickly because the models are constantly retrained on new data being fine-tuned. And this data comes from a large number of training factors. And this is all based on pathways. But it's actually a very brutal way of making progress because it's only going to address one query at a time. And in fact, even if you look at the query as a stack, if you rename something, or break something, it starts written, it's constant gain of document. And it's very, very reliant on the data. So what we show you simply LLMs they're capable to do any text, and there's a tremendous result on example. On the other hand, the system is very, very basic minded. And in many cases, they're used. So how do you resolve this challenge? Well, to solve it, you have to understand that scale and benchmarks is not the primary way that you should look at reality. Here are some concepts to get into. The first thing to do is the distinction between static skills that you memorize and fluid the ability to new programs on the fly to adapt to something that something is not prepared for. So there's a difference between having this big sponge of memorized facts versus being able to decide. And it's not a binary, it's a continuum, there's a spectrum between the two, but there's higher intelligence, higher ability to adapt on the right side of the background. The second concept is operational learning. The big difference between being still only in situations that are very close versus being still in general that are going to walk through it. For instance, if you know how to add numbers, you should be able to add any two numbers, not just numbers that you see and if you know how to solve speed-up factor, you should be able to solve it for any value of n, not just n equals 1, n equals 3, which by the way is exactly what happens with the element. You can solve speed-up factor not for n equals 7 because it's not balance between triangles. But then there's a section that you can have integration area that's more like a graph, there's high integration on the right side. Lastly, you should ask about information efficiency. How much information, how much data was required for your AI system to require a new skill, and higher information efficiency for process with higher efficiency. And all these quantities, all the both streams are linked by a central concept, which is the concept of generalization. Generalization is very much the central problem in AI, not benchmarks. In generalization, you all know experience that is common. It's basically to handle situations or problems that differ from what you see. So it's fundamentally the ability to be novelty, certainty, the ability to stay autonomy, the ability to adapt, change. And this is precisely what you need intelligence for. If you were able to only encounter situations that were already prepared for your original question, then you don't actually need it. You should be finding an insight, which is half of the given. But what you gave us is already the optimal thing. Intelligence is really fast, how to adapt on the fly to something like that. And this is precisely the reason why an example with the AI systems that are here. This example were not designed with generalization. Or rather, they were designed according to different populates functions for generalization. Most examples do that you have already exam questions and answers beforehand. And assume that the question being asked is somewhat deterministic. And it doesn't really start from LLM. The LLM actually provides most of the information. And it's true, unless you're talking about the pure memorization exam, in which case it's really not surprising to get a lot of classes because it doesn't memorize most of the time. We want AI as the ability to adapt, generalize new skills. And to get there, we need a way to measure it. It's by measuring generalization that we be able to know where we are and make progress. It can serve as a feedback system. And to start measuring this, really generalization characterizes the relationship between information you have, which is your prior knowledge and your past experience, like trained data, and your operational data, situation space. And because there are people situations that have to go with identity, they're going to feature uncertainty that technology. And the quantification of generalization efficiency with which you operationalize past information in order to deal with the future. You can calculate it as a conversion ratio. The higher the conversion ratio is, the more intelligent you are. So if you like me, you can use algorithmic information theory to try to decide the normalize and quantify the structure. So I have a paper about it, and one of the things that the paper is to measure generalization power is possible for priors and experience because you're talking about conversion rate, so what we on the name. And specifically interested in comparing AI intelligence then you should rely on human-like priors, something core knowledge. The perspective let us think about core knowledge. Let us balance the progress. So I'm not going to be doing myself. As an attempt to fulfill these requirements for what should be a good benchmark on intelligence, so I created the abstraction and using importance of intelligence that and I think it's more by AI. And you can see it as a program benchmark, but you can also see it as a also it's the journey. And the key idea in R is that every task in order to solve them, steps you basically cannot prepare in advance for R. And it tries to control for expense in the sense that you're doing few-shot programming. You're trying to figure out how to perform a task, even just like 3 examples. And it's controls for clients in the sense that R is entirely grounded in core knowledge. So it's not supposed to be any required knowledge but methods. Instructions of just core knowledge system, object has allocation constant. And the running game challenge on this one is quite several characters about all things not in one sentence in the matter. The right has state-of-the-art compound and for 30% of this task story. The joint is very stuff because and so this is from before the LLMs for content mentioned. But today there's actually a lot more interest in art further than this. And it's very interesting. This is a bit more. And there are many papers of some art first members for LLMs on the major portion. And the members that different reports often some issues on the doctors, sometimes the watches the transit right into now everyone curriculum tasks demonstrates some concepts from knowledge in parts of the application. So if you really report the first, the validation step, we also have to run accuracy on the selected set of tasks. Elements is part of the change. But if you get to the top, what you see is that direct prompting of LLM GPT for Gemini is going to get you 5 to 10% test difference. Compared to a state of the art about 30%, which is achieved with the program instruction, and we'll go into the control. So this is very interesting, right? Like LLMs don't seem to be start with the next part of focuses on the ability to handle something that is not in control. But at the same time, we do seem to have a non-zero intelligence, and that's very interesting. Right? So I think we have to keep in mind that the benchmark of the is very far from perfect. There's a chance that you could achieve this 5 to 10% by horizon things. It's possible. We have to investigate where this reference comes from. Because if it comes from something that looks like reasoning, then you can imagine, you can scale it up and eventually get it right. On the other hand, it just recites and memorize pattern. Then you're not going to get there. Then it's stuck by your game. That brings us to the problem of abstraction. Abstraction and generalization are closely tied together because abstraction is the engine through which you produce generalization. So we should investigate abstraction in general, how it's produced and how it's produced in LLMs about it, and so on. And so it's not a dynamic question. So let's take a look at abstraction. And to understand abstraction, you have to start with the universe. So an interesting observation about the universe is that it's made of many different things that are all similar, all analogous to each other. Like one human is similar to another human with shared origin. One tree is similar to another tree, is also similar to a neuron. electromagnetism is similar to gravity, isomorphic to gravity. We are surrounded by isomorphisms. So I call this the kaleidoscope hypothesis. You all know what the kaleidoscope is. It's a tube with a tube, it's a colored glass in it, and a set of mirrors, and the mirrors are going to repeat amplified that it is a glass to create these remarkably rich complex patterns out of just a few channels of different information, which are the glass. And intelligence is the ability to combine the experience graph, information graph, to find bits that are reusable. Then you extract the bits, and once extracted, you put them in abstractions. And they take the form of programs or representations, and you can reduce them to make sense of novel situations in the future. And intelligence is basically the ability to abstract analysis. And I believe that in fact, pretty much all there is to have a high sensitivity to analogy, you'll be able to extract powerful abstractions from little extent, and you'll be able to use them to cover a maximally large operational area of future experience space. In future situations, even there is a lot. One really important thing to point that abstraction is not binary ability where either for the good of it or not. It's very much a continuum. There's a spectrum from memorized factories to organize knowledge that we generalize a bit better, to models that we generalize strongly, to meta models, the ability to publish models on the fly, to finally the discrete efficiency. P0 is when you purely memorize point-wise factors like this. So they are presented as functions, we'll see why in a second. And there's no abstraction basically here at all. Your factors are not going to generalize fast exactly what you memorize, which is why these functions that you're arguing and abstract. Once you have many factors, you can start organizing them into something that may generalize a bit better than purely the set factors. So here you have a more abstract function. It takes an argument which abstracts for x, because x could be anything. And the thing with this kind of organized knowledge is that because it's based on either complex factories or interpolation between complex factors, it's not going to generalize yet. Extraction is weak. It may be inaccurate, it may not work on little points that are thought on what you see. The next degree is to turn the knowledge into abstract models. So a model is not going to encode factories anymore, or interpolation between factors. It's basically going to encode a concise way of processing your inputs to get results. So here our model position is an accuracy expressed in terms of binary operators. And what's nice about it is that it's always going to return the right input, no matter the input. So it's a very concise. It's a strong abstraction. It will be operational in a very large input space. In fact, anything. And this is where LLMs see for. The next stage is the ability to generate models automatically. That's how you're going to be able to handle novelty. That's what intelligence really is. And the last stage is useful in a way that's going to be maximally information. Be able to master new tasks with very good experience, very good information. And not only are you going to display high skill in this task, and that model you're applying is very abstract, advisable, but you'll be able to develop that model using just a few terms. That's very much the holy grail of AI and the reciprocal problem. We can only have secret LLMs on the spectrum. I believe there's somewhere between optimized knowledge and generalizable models. We are clearly not quite at the model stage yet, because if we were at the model stage, then you could add numbers of sort with LLMs, or you can infer that A is B, also and B. But at the same time, it's clearly not just a database of complex factors. LLMs can generalize to things that are in fact pretty far from that same distribution. It's some form of organized knowledge slash conquest model that doesn't drive. And the thing is, if you solve all the problems that plague eventually, like hallucination, wakefulness, realization issues, you're going to get to the next step, which is the model stage. But if you want to get to the stage after that, on the fly model synthesis, there's a massive jump. It's not going to be enough to just scale up the front approach. You need something, you need to change direction. So, in order to figure out, what should be the direction, what are the missing? Yes, it's taking how abstraction works. So I say that intelligence is sensitive to abstract knowledge. And there's more than one way to draw analogies. How many ways? I believe you have two categories of analogies from which arise two key categories of abstraction. And they're pretty similar to each other, they mirror each other. So both are about comparing things and merging these individual things into common abstraction prototypes by eliminating certain depth about the original. You take a bunch of things, you compare them, you drop a stuff that doesn't matter. What you're left with is an abstraction. And the key between the theories is that there's one that can compare things via a continuous function. So it operates in a constant domain. And this is what that perception, intuition, cognition. And meanwhile, the other one, program-centric abstraction, is not going to look at distant functions. It's going to be comparing discrete programs, which is discrete graphs. It's going to be looking not for similarity, but for exact matches between subgraphs, for exact subgraph isomorphisms. And this is similar to human reasoning of planning. It's so what software engineers do. Like if you hear a software engineer talk about abstraction, this is exactly what they mean. Identify things that are exact subgraph isomorphisms and abstracting them away into class of functions. So most of these forms of abstraction are driven by analogy making. Analogy is very much the engine that produces abstraction, but it can be the value analogy or program analogy. And value analogy is geometrically grounded about comparing things like how similar they are in a continuous way. And the other one is and I really believe that all cognition arises from a combination of these two forms of abstraction. And you can remember them, the left brain versus right brain analogy, which of course, you have to find it's metaphor. It's not actually the way the visualization thing. It's an image. And of course, you probably noticed this also here. The type 1 thinking versus type 2 thinking from timeline. So, what about elements? Like, how do elements implement abstraction? And do you think elements type 1 or type 2? That's the question. So, to understand what elements are doing, I think we can benefit from looking at a much simpler but less powerful, yet pretty similar system, which also keeps the highly structured mechanism. You can look at Word2Vec. So, we could have 2013, 1 decade ago. Word2Vec looks at tokens that occur in a certain window, like a sentence, and it tries to maximize their dot product so that words that are correlated should only be embedded further together in the token space. And remarkably, it turns out that if you do this, in the implicitly learning useful semantic functions, vector functions that meaning. And this is emergent learning because when trying to learn stuff, like there's going to be a vector interface where if you add it to new forms, all forms that is the right thing. Or it can give you like the first version of the dot. And what do elements do really? Well, they do basically the same. So just like Word2Vec, they vector embedding space tokens, and just like Word2Vec, they organize the space based on the dot product between vectors as the measure of their similarity. And the big difference is that the work to make with the shadow model, they actually a model actually basically the statistical has equivalent of regression. And meanwhile, elements of course they did models that don't just learn one, they actually see gradually more refined spaces. If they can encode extremely complex and extremely nonlinear functions. The transformer, the most important bit, the most important component, is the self-retention mechanism. Self-retention is a way to learn a new space of tokens by linearly combining tokens on the previous space in this case. And this is done in such a way that tokens with a high dot product end up getting progressively closer together because they express the next token are going to be expressed as the combination of the first token, the similar tokens of a higher weight. That's the kind of heading learning in infancy. Because things that co-occur together are gradually encoded close together. And so just like most of that, if you do this, you end up with emergent training, where your embedding set is going to end up storing really complex and really vector functions. Much more complex than what that can be like write this instead of Shakespeare. Is a vector function is implicitly learning when you're training this model. And yeah, so it's all learning implicitly just because we are trying to organize the space of words using this sort of like agent learning type mechanism implemented by self-attention. And this is really chemical type 1 abstraction, where you're grouping similar items together according to continuous instructions, the dot product in this case. And then you're going to next group the two items based on distance from class items and interpolation between representation and relationship of class items. This is definitionally type 1. And transformers are really great at it. They're great at type 1 abstraction. They can do everything it's expected for perception, intuition, and pattern recognition. In that sense, they are a major breakthrough in AI. But they are not good fits for type 2, and this is where all the limitations we discussed come from. This is why you cannot add numbers. So how do you move forward? How do you add types into your models? How do you start solving up with LLMs? And the answer is you have to leverage discrete program search. Discrete program search it's very, very different from the deep learning approach where we continuous spaces learning from this. It's basically an entirely separate branch of complex kinds. And we actually merge it with the products. So where's discrete program search? Combinatorial search of a graph of operatives that you take from a domain-specific language, so DSL. And there are many things you could do. There are many flavors of the idea, like generative programming, for instance. To really understand it and contrast it with deep learning, you can draw this analogy. So with learning, the model is going to be functional function in program synthesis. Graph discrete characters. In deep learning, the learning engine is very understand. In program synthesis, combinatorial search, you depend feedback signal is a continuous loss function. In program synthesis, it will be an exact correctness check. Does your graph actually produce outputs? And in deep learning, the key challenge is really obtaining a dense sampling of the data distribution with enormous amounts of data. And with the program synthesis, the challenge is actually combinatorial explosion. Your search space blows up at the problem side very quickly. And program synthesis is very successful now. In fact, it's state of the art. And you have to keep in mind that these are just baby steps. The system considered around this at scale. They're not doing much structuring. But yet, the thing that is the state of the art today is basically obtaining unbound program synthesis approaches in one system in the system, which is going to have still far from from university. So let's go back to the problem of generative abstraction. The way you can try to abstraction in program synthesis. So you start by solving problems just by searching various data. You're combining operators, coming up with programs, and you're looking at programs that actually produce so much about. And then you're going to start looking at subgraph isomorphisms in your programs. So both using a single program, like you're going to do refactors, find places where you're repeating yourself, in that way. And also fast programs. And when you find them, you just create new functions. And you store them somewhere. You add them back to your dear set so that the next time you do a program search, you can start reusing them. And this is actually very similar to software engineering. It's like you have a detail of stored programs. And the reason why software engineering is complex programs is damage because they have access to this level of repository of predefined functions and libraries. And this is really a systematic implementation path to abstraction. So now we know what the implicit elements are, we know what they're good at, we know what they're not good at, we know that the Python abstraction is very useful, but it's actually only one part of what we do. Where do we go next? So I said earlier that I believe intelligence is a combination of Python and Python, two concepts actually. And you cannot go very far if you're just a version of one of them. You really have to combine them to see that potential. And this also really human intelligence shine. That's what makes you special. You're very good at combining perception, intuition, and reasoning and planning on you. We combine those forms of practice, and this is we should take AI next. So, how to do that? In order to training for a problem, the first thing that the problem space that is interpreted. It's not in lots of it. And if you look, for instance, at the single R class, it's not interpreted and it only has three examples. You're not going to be able to. But what else? And we're also not going to be able to really define the memorize pattern because the entire purpose of R is that you should not be able to provide solutions to the task of the entire number. However, if you take one step back, one step down the scale of abstraction, and you look at core knowledge system, which the R is built on, each core knowledge system is interpolated in it. And it could be learned from data. And also you actually have the ability to collect lots of data from it. So you could start using deep learning to parse the world into objects, concepts, data tunes and do this problem. Instead of inputs for forms that may be looking at each classroom will do. And likewise, if you take a step up, if you look at the space of all tasks, there you will find this mechanism regularity. You find that the space of tasks has a smart continuous structure. And because your lifetime is an continuous tasks, then you actually have a reasonable amount of data. And you can start with Python thinking on that and start applying to training there. And one thing about reasoning in humans that it's very much enlarged the way we do program synthesis and brute force iteration. Reasoning in humans is very much guided by high-level intuition. And I think this is because one problem in program synthesis is the complexity of the search, the fact that the search is most problems. And so today our two exciting research areas to combine the strength of program synthesis. The first one is programs that incorporate different components or the levers. And this is something I've been looking at for a long time, but nowadays starts to be practice in the form of LLMs that are implemented. This is the symbolic tools, already happening. And the other avenue is to use these training models inform discrete program setting, efficiency of discrete program setting instead of using USB. You can use deep learning, for instance, as a perception layer to process situation discrete building blocks that include program system engine. Or you can use it as a driver, as a guide for a program system process to basically give you program sketches and stuff with each time the happen in the stage and all the branches that should be put. And you should keep in mind that human engineers, for instance, software engineers who don't program the way that programs in the engine today. People rely a lot on intuitive machine, but they only start applying step-by-step reasoning once they are very achieved left. And I really believe this is what we're going to see in AI systems. We have step-by-step reasoning processes, guided by equal power from the perception. And a very early example of what this might look like is this paper, hypothesis search language models. Really like it. Basically, using an LLM to guide a Python program search process. They're using an LLM on our tasks to provide natural language description and tasks on hypothesis, natural language about what the problem might be. And then they're using the LLM to translate this natural language hypothesis into Python program, and then they check correctness. And they're actually getting 2x performance power. And you get 2x performance on anything that's you get. First one, something like okay, I leave you with quotes from Marvin Minsky, very much close. What we're hearing today about right and PCI. Which way to machine with general intelligence, the human beings is not 2023, 1970. And the counter quotes from Kelsey, 36 years later, human evolution is modern scheme in 1950. We talked about the insightful speech. Any questions?
Thank you very much for the inspiring talk. So, I have a question regarding the model from Google as well. And the takeaway message from this is if you scale up your model and your data, you can learn new tasks that the model was not trained on, which contradicts the perspective that you showed for the AGI. So my question is, how would you place the problem model on AGI spectrum that you showed? Right.
I do not believe it's at the model stage. I really think that what you're seeing in practice is that François don't handle compositionality very well. If you want to start solving problems that you genuinely not seen before, then you have to do compositionality of atoms that you have installed. So the way you can think about models is that they're sponges of patterns that were mined from human-generated data. And for that reason, they're very much limited by the kind of patterns that can be found in the data. If you go outside of that scope, they're not going to be able to operate. Even if you're just looking at relatively simple compositions of known patterns, these models can identify. And one thing is that, of course, you can scale these models up. And scaling them up will basically keep paying off, because if you have a bigger sponge trying to mine more data, then it's going to be storing more patterns. It's going to be covering a broader scope of problems. So you're going to, in a way, increase its generality, but only in the very analysis, because it's still going to be bound by the fact that it cannot go beyond the patterns found in the data. So basically, you need more than just the ability to store patterns, you need to generate your own. And the only way to do so is search.
Yeah, thank you. Next question. Very interesting thought. So my question is, for the human, we have this standard that humans are expert in one specific domain. For example, you have a very knowledgeable lawyer or physician or neuroscientist. So do you see in future you also have in AI something like a specialized agent which are really intelligent in that field of work, and in this field you have like an AI which is like an aggregation of different agents which each one of them is perfect in reasoning in one domain, and overall we have general AI but having sub agents rather than like one big agent which is generally intelligent. Thank you.
Yeah, sure. I think that's entirely plausible. Specialization is good. Society's visions seem to be able to do things that you cannot do with one single agent. I think humanity is a pretty good example of that. One human is not that intelligent, but human is the fact that I can actually do. So it really makes the start seeing this.
Thank you very much. And another question is regarding multimodality. Do you think multimodality is helpful for abstraction and refinement for AGI? And if so, will it be most helpful for type 1 abstraction or type 2 abstraction? Thank you.
That's a good question. Yes, I think exactly two exactly the same. But it's not going to help you start with. It's not going to help you start with. The reason why cycle is benefit because you start mining more modalities, you start mining images, you start mining sound, videos, with access to an entirely new category of patterns. Then you can notice, encode, fractionalize, reduce, and you can, because it's a different modality, it's only going to partially overlap to balance the point like in language. And if you look at the way humans handle information, it's kind of much more right? We use it in language, visual information. That when you use the math problem, all some abstraction in addition to it, and no lines. And if you start training all of the big transformers and more modalities, they will solving it the same thing. But again, with the sort of hard limits that they are not going to be able to go beyond the patterns in one from as zero. Again, if you really want to go beyond that, you need to be special.